In this section, we talk about commonly used modules. These are the modules you'll use day to day. We'll introduce the modules, show how they're used in practice, and also give tips and tricks for certain modules. Let's start by looking at what data types are available. So all the sample values in AudioWeaver are 32-bit. And so there's three fundamental data types that we deal with. There's floating point data, there's integer data, and there's also what's called FRAC32. We're going to learn a little bit more about that. We can also represent Boolean signals as integers. So we'll represent it either as a 1 or a 0, being true or false. There's also separate modules for handling different data types. So on the right, you'll see there's a sync display. So there's a floating point one. That one's unlabeled. You can think of that as the default. There's a FRAC32 and an integer one. What also happens in AudioWeaver, all the input and output data to your layout is all FRAC32 data. That's all the data coming from the I/O and out to the I/O is FRAC32 data. So let's learn a little bit more about FRAC32 data. So the range of integers goes from -2 to the 31 up to almost 2 to the plus 31. FRAC32 samples are integers, but we conceptually scale them by 1 over 2 to the 31. So that means that the range of FRAC32 values goes from -1 to almost +1. Okay? Anything outside this range is going to clip. So if you're converting from float to FRAC32, you have to make sure that the sample values are in the allowable range or they're going to clip. All audio I/O in AudioWeaver comes in and goes out as FRAC32 samples. Now, if your codec has fewer bits, so suppose you have a 16-bit codec, then the audio data is going to be placed in the high bits of each 32-bit word into the most significant bits. So if you have a 16-bit codec or a 20-bit codec, conceptually it's still in the range plus or minus 1. Now, usually you want to do your processing as floating point or some other data type. So you're going to use the type convert module to make changes between data types. Let's look at basic signal management, starting off with type convert. So this module can convert between any of the three data types. Now the input data type is inherited from the connecting wire, and then you specify the output data type as an argument. So in the example on the right, we have data coming in from the I/O pin as FRAC32, and then we specify as a module argument that we want to output floating point data. And so that'll configure the module to accept FRAC32 and then output floating point data. Another very commonly used modules are the interleave and de-interleave modules. So interleave converts mono channels to multi-channel, and de-interleave does the opposite. Takes a multi-channel signal, converts it to multiple mono signals. In both cases, you specify the number of channels or pins via arguments. So in the example on the right, both of them are specified as 2-channel, and you can specify any number of channels. Another interesting tip is that the interleave module doesn't just operate on mono inputs. In fact, you can give it any number of channels on each pin. For example, you might have 2 stereo signals coming into the interleave module, and it's going to output a 4-channel signal for you. Here's a typical interleave de-interleave example. So we have stereo data coming in, de-interleave into 2 mono channels, we delay the left channel, and then recombine to stereo, and then send it out the output pin. Another important module is the router module. Conceptually, it copies channels from one wire to another, and it's useful for extracting, combining channels. You can basically reorder them at will. Now in this module, you specify the number of input pins as a module argument. The module has 1 output pin, and you specify the number of output channels as an argument. The input to output channel mapping is set by the inspector, and this is truly one of the most useful and underused modules in AudioWeaver Designer. The example on the right shows you how to split a 6-channel input into 3 separate stereo pairs. So the input to each of the routers is a 6-channel signal, and that represents 3 stereo sources. So the first router, select A, selects channels 1 and 2. Select B selects channels 3 and 4. And the last one selects channels 5 and 6. After that, we have a multiplexer module which selects one of the sources as the output. So for example, you might select between radio, Bluetooth, and some other streaming source there. And then you smoothly switch between them with the multiplexer. So this is one example of how to use the router module. Let me give you another example here. Now, suppose you have a system where you're only interested in the last 4 channels. So the system has 8 input channels, and you want to deal with the last 4 channels. One possibility is you could get an 8-channel de-interleaver module. The first 4 channels are ignored, so we attach those to a null sync, and then the last 4 channels we interleave, and then we process as desired. Yes, this works, but this is a very inefficient implementation. Let's see how to do this with the router. Okay. On the router, we specify 1 input pin and then 4 output channels. And then on the inspector, we specify channels 5, 6, 7, and 8. So this will take the 8-channel input, select 4 of the channels, and copy those to the output wire. Let's do another example. Okay. Suppose in addition to those 8 input channels, there's another input which is a sine wave generator. In this case, I specify 2 input pins. Each pin can have a different number of channels, and then the channel mapping will now allow me to select any of the channels on pin 1 or pin 2. So this is the router module. You'll use that every day you're using AudioWeaver. Another module that's frequently used is the multiplexer. Okay. Multiplexer will allow you to do A/B comparisons, so it'll smoothly switch between different inputs. Okay. Each input can have multi-channel, so you can switch from one stereo source to another stereo source. Different ways you can configure this. First of all, you specify the number of input pins as an argument. Here we're comparing A versus B, but you could have 3 things and compare A versus B versus C. There's an optional control pin if you want to do the selecting based on a control signal. And then you can specify also 2 things. One is the smoothing time, which that controls the ramping speed between the channels. And there's also a fade time, which is how much silence do you want between the transitions. So typically I set the fade time to 0 and then adjust the smoothing time. Usually I set the smoothing time 10 to 20 milliseconds so that there's no pops or clicks. Fade time you'll set to non-zero if you want to make it obvious when there's a transition happening. Here's another way you might use the multiplexer. You might enable or disable a feature. So in this case, maybe you want to enable the filter or disable the filter. In this case, the multiplexer has an option of 2 input pins to choose from. So it's a Boolean decision, either 0 or 1, so it draws a checkbox. Okay, so unchecked equals 0 means it selects the top path. Checked on the bottom means it selects the bottom path. Now you might be wondering, what's the advantage of doing it this way versus just bypassing the second order filter? Well, with bypassing, you get an abrupt start and stop of the audio processing, so you can get pops and clicks. Whereas with the multiplexer, you can smoothly enable and disable the feature. Okay. I also want to note, when it's disabled, the filter on the bottom is still processing. It's just that the output isn't used. And then when you enable it, then it starts using the output of the filter. So this example shows what happens when there's 2 things to select from. When there's 3 or more, instead of a checkbox, you now get a drop list. And then that drop list will adjust based on the number of inputs and outputs you have. Other modules that are used are, there's a null sync module. So sometimes you have modules that you might not have finished building your complete block diagram, and there's modules with outputs that you want to tie off, which is basically just ignore those. So you would drag out a null sync module, and then you would attach modules to that. This module doesn't do anything. It's really just a terminator, and the data is discarded. Similarly, there's also a zero source module. Sometimes you might have unconnected module inputs, and to get the system to build, you'll have to feed some data to it, so it's convenient to use the zero source module. Zero source module, since it's a source module, as the arguments, you have to specify the output pin properties. So number of channels, block size, sample rate, and data type. The other thing is if the block size is empty, it'll take the block size of the system input pin if you're at the top level, or the block size of the first input pin of the subsystem. And same thing for the sample rate. So it can inherit block size and sample rate. Another useful feature are annotation modules. They basically allow you to put text on the canvas. You can document things. You can put lines on it, rectangles. You can point arrows at things. So this is nice for documenting a design. Another module is the marker module. Okay, this module has two purposes. First, it can be used to clean up wire routing as shown below. So AudioWeaver doesn't have the best wire drawing algorithm, so sometimes you want to route the wire specifically around some other modules in your layout. So the marker modules allow you to do that. And we'll see later that the marker module is also used when doing frequency response measurements. So it allows you to mark two wires in the system and do a frequency response measurement between those. Now the marker module is virtual, which means it only exists on the PC in your block diagram. When the system is built, the module is removed, so it doesn't take up any memory or any processing on the target. There's two options if you want to create a marker module. You can either drag it out from the module palette, or you can right-click on an empty part of the canvas and select Add Marker. Now let's talk about modules for modifying the gain. First ones are scalars. There's two very important ones. There's a general purpose scalar that has a single gain which is applied to all channels. The second one is called the general purpose vector scalar. Okay. This one will give you separate gains per channel, and the vector scalar will adapt and adjust to the number of channels you have. Each of these can be configured to be smoothed or unsmoothed. If it's smooth, it takes a little bit more processing time. You can also specify the smoothing time as a module property. You can configure it for linear or dB operation. dB is the default. And they can be with or without control pins. On the right, you can see example of the scalar module inspector. That's on the left. So there's a single gain applied in this case to both channels. On the right is the vector scalar. And now you can see there's multiple sliders. There's a master gain which is applied to all the channels. And then there's individual trim gains per channel. We also have smoothing in scalars. So smoothing will eliminate discontinuities when you make changes in the gain. And the smoothing that we have is performed on a sample by sample basis. Okay, it's not in the control thread, but it happens on a sample by sample basis. And we use first order IIR filters, and they're implemented quite efficiently on different processors. Now, they have a configurable smoothing time that you specify in milliseconds. And what happens is after one smoothing time, you'll achieve 63% of the gain change. And after 3 smoothing times, you'll get 95% of the gain change. The picture on the bottom shows you the smoothing that happens. So you'll see the instantaneous gain change. We go from 1 to 2. And then the blue line shows you after smoothing how the gain change isn't instantaneous, but it starts ramping towards the desired gain of 2. We call that the target gain. We also have modules for inverting signals. So that's essentially multiplying by +1 or -1. And the invert modules do it smoothly, so you can specify the smoothing time. So there's no pops or click when you invert the signal. And we have 2 versions. There's an invert module, okay, that inverts all the channels on a multi-channel wire. Or there's an invert N, where you can individually specify which of the channels are going to be inverted. Both of these modules include smoothing. There's also multiple modules for muting signals. And all of these operate smoothly. So you can specify the smoothing time and so forth. First one's the easiest one. It's the mute module. Okay. This either mutes or unmutes all the channels in a wire. Then there's a mute N. You can specify individual channels to mute. And finally, there's a solo mute, which is more complicated. You can either solo individual channels or you can mute them as well. So this is very useful, like in a home theater context where, hey, I just want to listen to the center channel, or I want to listen to one of the surrounds and so forth. So that's the solo mute. There's also mixer modules in AudioWeaver. And the mixer module, you specify the number of input pins, and each input pin can be multi-channel. The module has one output pin, and then you specify the number of channels on the output pin. So what happens is you might have a total of M input channels and then N output channels. And so the module has an internal matrix of size M by N, which are the linear gains. So that's the mapping from each of the input channels to each of the output channels. This module also contains built-in smoothing. Now let's talk about modules which are essentially filters that do equalization. The most frequently used module in this category is the second order filter. So this, under the hood, implements a biquad filter, but it has a number of built-in design equations. So instead of entering low-level filter coefficients, you can work at a high level. There's a total of 23 filter types as shown below. The module also has built-in smoothing, so there's not going to be any pops or clicks. And this is by far the most commonly used filter in AudioWeaver. Now, it's also important that you get to learn the filter types. So you'll see there's low-pass filters, high-pass filters, all-pass filters, shelving filters, peaking filters, notching filters, and so forth. Commonly used way to configure these is as tone controls. So what I'll do is I will use shelf filters as tone controls. So on the left, you have a low shelf. You specify the frequency and then the gain to apply. And on the right, you have a high shelf. And again, you specify the frequency and the gain. Another very commonly used filter type is the peaking filter. So you specify frequency gain in Q. And so you can accentuate or attenuate different frequencies in the spectrum. So this so far has been a single second order filter. There's also a module called second order filter cascade. And so this is N second order filters in series. And so this is nice for creating higher order equalizers. And what you'll do is you'll specify the number of stages in the filter as an argument. And then you'll have an individual set of inspector controls for each of the filter stages. So on the right, the inspector is for 4 filters. So you can specify any number of filters in this cascade implementation. So far, it's all been second order filters. There's also a Butterworth filter. And although the second order filters, you can do first and second order Butterworth filters, sometimes you need higher order filters. So that's where the Butterworth filter comes in. So you specify as an argument the filter order, and that'll essentially specify the slope of the roll-off. So for each order, it's essentially 6 dB per octave. And you can do anywhere between first order and 10th order filters. And then on the inspector control, you would specify the filter type, low pass, high pass, all pass, and then also the corner frequency. And both of those, filter type and frequency, can be changed at runtime. Another useful module is a 3-band tone control. So very often you want to be able to adjust low frequencies, middle frequencies, and high frequencies. And this is implemented as using both first order low shelf and high shelf filters. And together it's implemented as a second order biquad filter. So this is very efficient. On the inspector, you can adjust the gains. And on the property sheet, you can adjust the gains and also the frequencies between the cutoff frequencies between the 3 bands. Taking this a step further is the graphic EQ module. You can essentially specify the number of stages as an argument. Then you can specify the gain per stage. And you can also specify different order filters for each stage. So depending on how sharp you want it, anywhere from 4th to 12th order filters. So there's 1 filter per frequency band. Beyond this, there's a whole bunch of filters with design equations. Emphasis, pre-emphasis, de-emphasis filters. You specify the time constants. There's weighting filters. So if you want to do A weighting or C weighting for audio measurements, we have that. There's a pinking filter. It converts white noise to pink noise, and even a Hilbert transform. So all of these filters include built-in design equations, allowing you to easily use these modules. There's also all the standard filter types that accept raw coefficients. So this is if you're an expert user. So there's a 5 coefficient biquad, there's a biquad cascade, there's a biquad with smoothing, there's an N channel biquad, so you'll have different coefficients per channel. There's also FIR filters, sparse FIR filters. And if you use these filters, then you have to compute the filter coefficients yourself. And you can either do this from MATLAB, you could load them from a file, or you can also manually enter them on the inspector. It's also a set of high precision filters. These don't use a traditional biquad structure for processing. They still use 32-bit floating point math internally, and instead of typically 5 max per sample, they're using 7 max per sample. On the right shows an example of a low frequency peaking filter. So this is trying to do gain changes at 20 Hertz. So what you'll see in each plot, the one on the top is a standard floating point second order filter implementation. What you'll see is the noise floor is about 40 dB down. That would be audible. With the high precision filter, we're about 120 dB down. So we have variants of the high precision filter. They end in HP. So many of the filters that we looked at so far have their corresponding high precision versions. A lot of people ask me, when do I use the high precision filter? Okay. There's 2 places. One is you're running at a high sample rate. So 96 kilohertz, 192 kilohertz. If you're doing audiophile applications, then you should be using those. The other place is if you're doing low frequency changes, even at regular 48 kilohertz. If you're doing low frequency changes, say below 100 hertz, then it's good to use a high precision filter. Let's now look at modules for adding time delay. There's a sample delay module and a millisecond delay. They do the same thing, except one you specify the delay time in samples, the other one specified as milliseconds. Both modules accept multi-channel data, and these modules are not clickless. So if you make a delay change at runtime, you'll hear a pop or click. Now, each module allows you to vary the delay time at runtime, but what you have to do is you have to specify the maximum delay time in design mode as a module argument. So the one on the left is specified up to 100 samples of delay, and the one on the right is 10 milliseconds of delay. And again, you can vary that delay time at runtime as well. So these are the ones most often used. Also some other delays. There's a multi-channel delay. So you can have n channels, put a different delay per channel. There's a common pool of memory, and that can be split between the different channels, very frequently used in automotive. If you're tight on memory, there's a 16-bit delay. Uses internal quantization, so we only save the high 16 bits there. There's an n-tap delay. So you have a single delay buffer, and you might want to extract data at different delay times. This could be used for a reverb. And then there's also interpolated delay. This is used for time varying delays where you don't want to have pops or clicks. And this includes interpolation. Let's talk about different ways of displaying signals and monitoring the behavior. First module is the meter value. And so that's going to display signal levels in dB. This module can work on any number of channels, and the inspector is going to grow based on the number of channels that you have. You can usually use this module by default as the way it's configured, but the property sheet also allows you to change the time constants of the meter. Another module that's useful for inspecting data is the sync display module. What this module does is it copies data from the input wire to an internal buffer, and then the designer tools can read the data from the buffer and display it on an inspector as shown on the right. So this graphical scope display is very useful for debugging. On the right, you can also adjust between time domain, frequency domain. You can change your axis and scaling and so forth. So this is the sync display module. Earlier we saw the null sync, and the null sync in comparison doesn't have the internal buffer and it doesn't have the display capabilities. Another module that's very useful, that's used in conjunction with the sync display, is the rebuffer module. So the rebuffer module buffers up the input into larger overlapping blocks. You can think of it as a FIFO, as shown below. So on the module arguments, you specify the size of the output wire. If you give it a positive value, it would use that positive value as the buffer size. If you give it a negative value, then it would correspond to a multiplicative factor that multiplies the input block size. This module is often used in conjunction with the sync display in order to display larger portions of data. For example, on the right-hand side, you have a sine wave generator, which is essentially outputting one block of data of 1 millisecond, so it has 48 samples. So on the top, you would see, on sync 1, you would see 48 samples, which is 1 millisecond. Now suppose you wanted to see 4 milliseconds of data. Well, what you do then, you add a rebuffer module, and you specify an output size of 192 samples, and then that's a FIFO. We buffer up 4 blocks of data. So every time a new input data comes in, we output a complete block of data. And then you'll be able to see, in this case, 2 periods of the sine wave as shown below. So that'll give you 4 milliseconds of data. Sync Inspector can also change between time domain and frequency domain. So if you're showing frequency domain data, it's essentially reading the time domain data from the target, and that does the FFT on the PC inside of Designer. There's also an update button, so you can kind of freeze plotting if you see something of interest, and there's kind of full control over the X and Y axes and so forth. Here's another trick you can do with the sync module. Sometimes you want to look over a much longer time interval, say several seconds, but you're not that interested to see every sample value. What you might do in this case is I have an RMS module, so I take 2 milliseconds of data, I compute the RMS, and then I output 1 sample. So the incoming data has a block size of 96 samples at 48 kilohertz, so it's 2 milliseconds. Every 2 milliseconds, I output an RMS measurement. So the output is a control signal of size 1 that has a sample rate of 500 hertz. And in this example, I'm converting to dB. I'm adding an offset of 132, and then I'm rebuffering to an output size of 2,000 samples. So in this case, the output buffer is going to show the equivalent of 4 seconds of data. And this is what you might do to compute the SPL value. So that offset of 132 is the microphone AOP that gets added. So this display will update and kind of scroll in real time, and it'll show you 4 seconds of data. Now let's look at different ways that we can measure data. Useful module is called block statistics. What this module does, it takes a block of data and it computes a single statistic per block. So it's going to output 1 value per block and essentially outputs a control signal and effectively decimates the signal like we just saw. You can specify the statistic type. Maybe you want to know the maximum value or the minimum value or the max apps, which means we're going to take the absolute value, take the maximum value, and so forth. This module has no state, so it takes whatever it sees on the input wire over all the sample values, across all the channels, and it'll compute the specified statistics. So block statistics works across all the channels. There's also a block statistics N, which is going to have an N channel output and compute the statistic value per each channel. A related module is called subblock statistics. It's similar to block statistics, but it divides the input into smaller subblocks. For example, suppose you have an input block size of 256 samples. If you use the block statistics, it's going to compute that statistic over all 256 samples. What you could do with subblock statistics is specify the subblock size to be 32 samples. What it'll do is it'll then take groups of 32 samples of the input signal, compute the statistics, and then output one sample for each 32 samples. So it's effectively decimating by 32 in this case. And then your output wire is going to have a total of 8 samples. What you use this for? Maybe you have a partially decimated display. It's also useful for more efficient compressor limiter implementations. So far, the statistics modules we looked at were all stateless. The running statistic module, on the other hand, computes the statistic from the start of playback. So, for example, you might want to answer the question, what's the largest signal seen up until this point at a particular place in your signal chain? So, running statistics will track that for you. There's also a useful reset button. So you can reset while running, and then it'll start the calculations again. Another useful module is the root mean square, the RMS module. So this does energy calculations together with first order smoothing. So the way the logic works is first it squares all the samples in the input buffer, computes the average energy, so it sums them up, divides by the block size, and then it takes that, filters it by a first order low pass filter with a specified time constant, and then on the output it takes the square root. So this module again takes a block of input data and outputs one value. There's also a related RMS-N module which computes a separate RMS value per input channel. So example above is a 2-channel SPL meter. You can specify the weighting filter. If you want A weighting or C weighting, you do an RMS calculation. By changing the smoothing time, you can switch between fast averaging and slow averaging, convert to dB, and then convert to SPL. Let's talk about different signal sources. These are really signal generators. It's wide variety. You can output constant values, periodic values like sine waves, and also random sources like white noise or pink noise. Since it's a source module, you have to specify the output wire properties. It can't inherit those. So you have to specify the block size, the number of channels, the sample rate, and in some cases, is it complex or not. Typically, the modules can inherit the block size and the sample rate from the input to the system or to the subsystem that it's in. There's also a few modules in AudioWeaver which are wave players. There's a buffer source module, so that contains one block of audio data and continuously outputs that same block of information. Another one's a periodic source. So this is a larger circular buffer. You specify the buffer size, and then it'll output smaller blocks from that data and also loop at the end. And finally, there's a one-shot player. This module has an internal wave samples, and then it plays the wave data when it's triggered. So the module has a trigger pin, so it's a Boolean signal, and it also has a controllable playback pitch on the F ratio pin, so you can control that at runtime.